Our reality might be a cosmic fluke, one fragile possibility among an infinity of others. This is the unsettling and thrilling realm of quantum realities, where the solid world we know dissolves into a sea of probabilities and parallel existences. By the end of this exploration, you will have journeyed through 30 distinct visions of existence that fundamentally challenge what you think is real. We will confront theories suggesting you are living countless other lives right now, that the universe is a projection from its edge, and that your own consciousness may be required to bring it all into being. How solid does your own world feel when you really stop to consider it? This branching begins with the smallest events imaginable. The theory of the many worlds interpretation was born from the mind of a graduate student named Hugh Everett in the 1950s, and it offers a radical solution to one of quantum mechanics' greatest puzzles. In the standard view, a particle exists in a haze of probability, a superposition of states until it is observed. At that moment of measurement, the wave function collapses and a single, definite reality is chosen. Everett asked a deceptively simple question. What if that collapse never happens? What if instead every possible outcome of a quantum event actually occurs, but each one plays out in its own separate, newly created universe? To understand this, we must revisit the most famous thought experiment in physics, but see it through Everett's eyes. Schrödinger's cat. A cat is placed in a sealed box with a device that has a 50-50 chance of releasing poison, triggered by the random decay of a single radioactive atom. According to the old rules, until we open the box, the cat is suspended in a bizarre state of being both alive and dead. Only our observation forces nature to decide. The many worlds interpretation rejects this strange suspension. It says the atom both decays and does not decay. In the very instant that quantum possibility becomes a reality, the universe splits. In one new, equally real branch of reality, the atom decayed, the poison was released, and the cat did not survive. In another, completely separate branch, the atom remained stable, and the cat is perfectly fine. Both outcomes are 100% real. There is no paradox, only a cosmic duplication of history. This means the need for a mysterious observer to collapse the wave function vanishes. The universe is not waiting for us to look, it is simply proliferating endlessly at every quantum junction. Now consider the scale of this. Every particle everywhere is undergoing quantum events constantly. Every flicker of possibility, from the path of an electron to the spin of a photon, becomes a fork in the road of reality. The number of new universes blossoming from this moment alone is a number so vast it defies human comprehension. And within this infinite ensemble, every physically possible history is being written. The implications for you and me are staggering. It suggests that free will is not about choosing a single path, but about which branch of a pre-existing multitude you happen to consciously experience. Every choice you agonize over, every chance encounter, every near miss, has a counterpart in another universe where the opposite happened. There is a version of you who took that different job, who married that other person, who turned left instead of right. Your identity is not a single thread, but a vast, branching tree of selves, each living out a complete and valid life in a world of its own. The person you are right now is just one leaf on that infinite tree, forever unaware of the whispering forest just beyond your perception. Yet this infinite branching is not the only story. For decades before Everett's radical proposal, a very different framework held sway. One that accepts a fundamental uncertainty at the heart of existence. This is the Copenhagen interpretation, the orthodox view shaped by pioneers like Niels Bohr and Werner Heisenberg. Its core tenet is both simple and profoundly strange. Particles do not have definite properties until they are measured. Before observation, an electron is not in a specific place, nor does it have a specific momentum. It exists as a cloud of probability, a mathematical wave of potential. Only when a conscious observer or a measuring device that ultimately leads to a conscious observer interacts with the system does this wave function collapse into a single, concrete reality. This is not a physical splitting, but a sudden, irreversible selection. Think of it not as a tree endlessly branching, but as a single, shimmering mirage that solidifies into one specific shape the moment you reach out to touch it. The famous uncertainty principle, also born from this view, reinforces this intrinsic fuzziness. It states that you cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely you pin down one, the more wildly uncertain the other becomes. This is not a limitation of our instruments, but a fundamental feature of reality itself. The universe at its core refuses to be fully pinned down. The philosophical implications here are dizzying. The Copenhagen interpretation places the observer in a privileged, almost mystical role. It suggests that our act of looking is not passive but participatory. We are not merely discovering a pre-existing reality. We are, in some essential way, completing it. This stands in stark contrast to the many worlds view, where observers are just along for the ride in a reality that splits regardless of their presence. Copenhagen offers a single, shared reality, but one that remains indefinite and dreamlike until consciousness forces it to make up its mind. It is a more pragmatic approach for making calculations and predictions, but it leaves us with a deep, lingering question. What or who qualifies as an observer? Is a cat in a box an observer? Is a camera, or does it require a human mind? The interpretation is famously silent on this point, offering a mathematical formalism that works spectacularly well, while leaving the deepest mystery of what is really happening untouched. It presents a universe that is not a solid clockwork, but a conversation, a negotiation between the possible and the actual, with our own awareness as the final, decisive word. But if every possible outcome exists in its own branch, then what happens to you when you face certain death? This leads us to a startling and deeply personal corollary of the many worlds interpretation known as quantum immortality. It is not a theory in the traditional scientific sense, but a profound and unsettling thought experiment that follows the logic of endless branching to its ultimate, chilling conclusion. Imagine you are the subject in a modified version of Schrödinger's experiment. You are placed before a device that is triggered by a single quantum event, like the decay of an atom. If the atom decays within a set time, the device fires a lethal bullet. If it does not decay, the device does nothing, and you live. According to the many worlds view, at the moment of the trigger, the universe splits. In one branch, the atom decayed, and you meet a fatal end. In the other branch, it did not, and you walk away unharmed. Both branches are equally real. Now, here is the crucial twist. Your conscious experience, your subjective sense of being you, can only continue in the branches where you are alive to have that experience. From your own first-person perspective, you would never encounter the moment of your death in this experiment. You would only ever find yourself in the outcome where you survived. Every single time the device is triggered, the universe splits, and your awareness seamlessly follows the path of continued existence. To an outside observer, you might appear incredibly lucky, surviving against impossible odds over and over. But from the inside, there is no luck involved. It is simply the only reality you can ever know. This logic suggests a form of subjective immortality. No matter how dangerous the situation, there will always be some branch, however statistically improbable, where you survive. You might be in a plane crash, a terrible accident, or even face a terminal illness, and from your point of view, you would always find yourself in the universe where a miraculous recovery or escape occurred. The other yous, in the overwhelming majority of branches, perish, but you are never them. You are always the survivor. The philosophical and ethical rabbit holes this opens are bottomless. It forces us to question the very nature of death. Is death simply the end of a single conscious thread, while countless other versions of you carry on? It challenges our understanding of identity, suggesting that who you are is not a single entity, but a persistent point of view that hops across the branches of survival, forever leaving a trail of deceased counterparts in its wake. It also raises disturbing questions about aging and disease. Would you, subjectively, simply find yourself always in the branch where a cure was found, or where your body defied the odds? The theory offers no comfort, only a cold, logical puzzle that separates the objective reality of the multiverse from the subjective reality of a single consciousness navigating it. It presents a universe where, for the observer, the story never truly ends. It just continually forks onto the path where the page keeps turning. Yet this subjective immortality rests on a reality that might be far less substantial than it feels. What if the quantum strangeness we have been exploring, the branching paths and probabilistic fogs, are not features of a fundamental reality, but artifacts of something else entirely? This brings us to a theory that has leapt from philosophy into popular culture, the simulation hypothesis. Popularized by thinkers like Nick Bostrom and figures like Elon Musk, it proposes a staggering idea. Our universe, with all its quantum weirdness and mathematical elegance, is not base reality. It is a sophisticated computer simulation, a cosmic video game running on the hardware of a far more advanced civilization. The argument often begins with a simple logical progression. If any civilization reaches a post-human stage capable of creating vast, conscious simulations of its own ancestors, and if they have any interest in doing so, then the number of simulated universes would vastly outnumber the one original physical reality. Statistically, we are more likely to be living inside one of those countless simulations than in the sole, original base layer. The very laws of physics, upon closer inspection, seem to support this digital dream. Look at quantum mechanics itself. The idea that particles exist in superpositions of states, only collapsing into definiteness upon observation, mirrors exactly how a computer game renders graphics. To save processing power, a game engine does not calculate the precise details of every leaf on a distant tree until a player looks at it. It exists only as a low-resolution probability cloud until the observation command forces the system to render it in full. Our universe's quantum fuzziness could be a cosmic optimization technique. Even the fundamental limits of our reality hint at an underlying code. The Planck length, the smallest possible unit of space, and the Planck time, the smallest tick of the cosmic clock, could be the pixel size and processor speed of the simulation. Just as a digital screen cannot display anything smaller than a single pixel, our reality might be unable to resolve details below these scales because the simulation simply does not render them. The speed of light, the ultimate speed limit, could be the processing bandwidth limit of the system, preventing information from moving so fast it crashes the program. So who are the simulators, and why would they run such an elaborate program? The possibilities are as vast as they are unsettling. They could be our own distant descendants, running ancestor simulations to understand their history or for pure entertainment. They could be an alien intelligence studying the evolution of consciousness. The simulation might even be a scientific experiment, a test of physical laws, or a training ground for young minds in a civilization we cannot fathom. Its purpose could be so alien that we, as entities within the program, lack the very concepts to understand it. This theory reframes every mystery. Dark matter and dark energy might not be exotic substances, but placeholder values or glitches in the cosmic code. Déjà vu could be a memory leak. Miracles might be admin privileges. The very fact that our universe is comprehensible through mathematics, a language that perfectly describes its behavior, suggests an underlying logical architecture, a set of programmed rules. We are not discovering the laws of nature, we are reverse engineering the source code of our own existence. The question then becomes not whether we are in a simulation, but what we do with that knowledge. Does it make our lives, our loves, our struggles any less real? Or does it add a profound, mysterious depth to every moment, knowing that we are part of a story so grand? Its authors are still writing the rules, but what if the simulation is not running on a distant computer, but is instead painted onto the very fabric of space itself? This leads us to one of the most profound and elegant theories in modern physics, the holographic principle. It proposes a truth about our universe so counterintuitive it feels like science fiction. All the information needed to describe everything within a three-dimensional volume of space, every star, every planet, every person, can be perfectly encoded on its two-dimensional boundary. Our rich three-dimensional reality, with all its depth and solidity, might be a grand illusion, a holographic projection from a flat, information-rich surface at the edge of the cosmos. The seeds of this idea were not planted in the study of simulations, but in the fiery hearts of black holes. When a star collapses into a black hole, it creates a point of infinite density, a singularity shrouded by an event horizon, a point of no return. In the 1970s, physicist Jacob Bekenstein made a startling connection. He realized that a black hole's event horizon has entropy. Entropy is a measure of disorder or information content. The larger the horizon's area, the greater the entropy. This was revolutionary because it meant the maximum amount of information any region of space can contain is not proportional to its volume but to the area of its surface. Think of it this way: imagine you are packing a suitcase. You might think the amount of stuff, the information you can fit inside depends on the full three-dimensional space of the suitcase. But the holographic principle suggests the limit is actually set by the two-dimensional area of the suitcase's lining. It is as if everything inside is just a clever rearrangement of data written on the inner surface. This insight was refined by physicists Gerard T. Hooft and Leonard Susskind, who gave the principle its name and its full, breathtaking scope. They argued that if the information about what falls into a black hole is not lost but is smeared across its event horizon, then perhaps this is a universal rule. Perhaps all of space obeys this law. Our entire universe, with its vast three-dimensional expanse, could be a hologram. The data that creates you, the device you are using right now, the distant galaxies, all of it could be encoded on a distant, two-dimensional surface that surrounds us, a cosmic film. We are not looking at a projection screen, we are living inside the projection. To grasp this, consider an ordinary hologram like the kind on a credit card. It is a flat, etched surface, but when light shines on it, it produces a stunning three-dimensional image that you can look around. The holographic principle suggests our universe operates on a similar, but vastly more complex scale. The true, fundamental reality is a vast, buzzing information field at the boundary of the observable universe. Every bit and qubit of data there interacts to generate the immersive, three-dimensional experience we call reality. The solidity of the floor beneath your feet, the warmth of sunlight, the sound of a voice, these are all incredibly convincing renderings of underlying data. This solves deep puzzles in physics. It elegantly reconciles the laws of gravity, which govern the large-scale structure of the universe, with the laws of quantum mechanics, which rule the tiny world of particles. In this view, gravity itself may not be a fundamental force, but an emergent phenomenon, a side effect of the way information is processed and projected from the boundary. We are not pushed together by a force, but drawn together by the intricate data processing of the cosmic hologram. So the next time you look at your reflection, consider a staggering possibility. You are not just looking at a person in a room. You might be witnessing the magnificent, real-time output of a universe-sized calculation, where your entire life, your memories, your consciousness, is a three-dimensional story being told on a two-dimensional stage at the edge of everything. The holographic universe presents a reality that is both profound and deeply interconnected, But there is another vision of multiplicity that operates on a truly cosmic scale. This theory does not branch from quantum choices, but from the very first moments of existence itself. It is the theory of the cosmic inflation multiverse, and it suggests our entire observable cosmos is just one lonely bubble in an infinite, frothing sea of other universes. The story begins not with particles, but with the vacuum of space. In the standard Big Bang model, the universe exploded from a singularity, but it left puzzling questions. Why is the cosmos so uniform in all directions? Why is space so flat? The theory of cosmic inflation, proposed by Alan Guth and others, provided an elegant answer. It posits that a fraction of a second after the beginning, space itself underwent a period of hyper-accelerated, exponential expansion. In an unimaginably tiny sliver of time, a region smaller than a proton was stretched to a size larger than our entire observable universe. This smoothed out wrinkles, flattened geometry, and set the stage for everything to come. But the most radical extension of this idea is eternal inflation. The process may not have stopped everywhere at once. Think of it like a pot of water coming to a boil. Our universe is one bubble that formed and stabilized, where inflation ended and allowed matter and stars to form. But outside our bubble, the inflationary energy field still rages, expanding at speeds far beyond light speed. In that eternally inflating background, new bubbles are constantly nucleating at random points, each one a new universe with its own Big Bang, forever out of reach from our own. We live in a cosmic foam where each bubble is a separate, self-contained universe, floating in an infinite, ever-growing meta-universe. The laws of physics within each bubble are not guaranteed to be the same. When a bubble universe forms, the inflationary energy decays into matter and radiation in a process that can randomly set the fundamental constants of nature. The strength of gravity, the mass of an electron, the charge of a proton, these are not universal truths but local bylaws. In one bubble, gravity might be so strong that stars form and burn out in an instant. In another, the nuclear forces might be too weak to ever bind atoms together. Most of these universes would be sterile, lifeless voids, incapable of supporting any complexity at all. This provides a powerful, if unsettling, answer to one of the greatest mysteries in science, the fine-tuning problem. Our universe seems improbably, perfectly calibrated for life. If the strength of the strong nuclear force were just a few % different, stars could not create carbon, the essential building block of life as we know it. If the cosmological constant, which drives the expansion of the universe, were slightly larger, galaxies would never have formed. The odds of all these dials being set to just the right values appear astronomically small. The cosmic inflation multiverse offers a cosmic lottery explanation. In an infinite foam of universes, every possible combination of physical constants will be realized somewhere. We do not live in a special, designed universe. We simply live in one of the rare bubbles where the numbers came out right for stars, planets, and eventually, observers to arise and ask the question. We are the inevitable product of a statistical inevitability in an infinite landscape. Our entire history, from the first hydrogen atoms to the neurons firing in your brain right now, is just one possible outcome written in the physics of a single, stable bubble. Adrift in a silent, infinite ocean of other possibilities, most of them eternally dark and empty. This cosmic foam of bubble universes is a breathtaking vision, but it emerges from the mathematics of cosmology. Could there be a deeper, more fundamental theory that not only predicts a multiverse, but explains the very fabric of these disparate realities from the ground up? This brings us to one of the most ambitious and mathematically beautiful frameworks in all of physics, string theory. Its central idea is a stunning reimagining of reality's smallest building blocks. Forget point-like particles, the dots of zero dimension. String theory proposes that at the tiniest conceivable scale, the fundamental constituents of the universe are not particles at all, but incredibly tiny, vibrating loops or strands of energy, one-dimensional strings. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, a single fundamental string can vibrate in different modes. One specific pattern of vibration gives rise to an electron, another distinct resonance creates a quark, another produces a photon, the particle of light. In this elegant picture, every particle and every force in nature is just a different note on the same cosmic instrument. The symphony of these vibrations is the universe we experience. But to make this symphony mathematically harmonious, string theory requires something extraordinary. These strings do not vibrate in the three spatial dimensions we know plus time. They require extra dimensions of space, curled up and hidden at scales so small we could never perceive them directly. Most versions of the theory demand 10 or 11 dimensions for the equations to work. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But as you get closer, you realize it has a second dimension, a circular cross-section curled tightly around its length. String theory suggests that at every point in our three-dimensional space, there are 6 or 7 additional spatial dimensions, similarly curled into intricate, microscopic shapes called Calabi-Yau manifolds. The specific geometry of these hidden dimensions determines how the strings within them can vibrate, and this is where the theory opens a door to an almost unimaginable plurality of worlds. The possible stable shapes for these extra dimensions are not unique. Calculations suggest there could be a truly astronomical number of possibilities, perhaps 10 to the power of 500. That is a 1 followed by 500 zeros, a number so vast it dwarfs the count of atoms in our observable universe. Each distinct geometric configuration corresponds to a different stable vacuum state, a different possible set of laws of physics. In one configuration, the strings vibrate in such a way that gravity is strong and electromagnetism is weak. In another, the masses of quarks are different, preventing atoms from ever forming. Each solution represents a potential universe with its own unique rulebook. This is known as the string theory landscape, a vast, abstract terrain of possible universes. Our cosmos, with its specific particle masses and force strength, is just one tiny valley in this colossal, mountainous landscape. We do not live in a specially tuned universe, but simply in one that is compatible with our existence. The landscape provides a potential physical mechanism for the cosmic inflation multiverse. Each bubble universe nucleating in that eternal inflationary sea could have its extra dimensions frozen into a different shape, locking in a different set of physical laws. String theory does not just allow for a multiverse, its internal logic seems to demand a near infinity of them. Yet this incredible explanatory power comes with a profound challenge. With 10 to the 500 possible universes, the theory risks predicting everything and therefore nothing. If every conceivable set of laws exists somewhere, how do we explain why our particular set is the one we observe? The answer may lie in the same anthropic reasoning as before. We can only find ourselves in a universe capable of producing complex structures like stars, planets, and ultimately, curious minds to ponder the strings. The landscape is not a map of what must be, but a catalogue of what could be, with our presence as the only clue to why this specific reality feels like home. The landscape of string theory offers a dizzying array of possible worlds, but it still places us as passive inhabitants of a pre-written script. What if our role is far more active, even creative? This brings us to one of the most mind-bending proposals in all of science, the participatory anthropic principle, championed by the legendary physicist John Archibald Wheeler. He took the observer's role from the Copenhagen interpretation and pushed it to its ultimate, universe-shaping conclusion. Wheeler did not just believe we observe the universe. He proposed that we, as conscious observers, are necessary to bring it into being. In his own words, we are not just bystanders on a cosmic journey, we are participants in giving the world tangible reality. The universe does not exist independently of us, waiting to be discovered. It comes into existence through the very act of observation in a grand, self-referencing loop. To grasp this, Wheeler devised a thought experiment that has since been translated into real laboratory tests, the delayed choice quantum eraser. Imagine a simple version of the classic double-slit experiment. Particles like photons or electrons are fired one at a time toward a barrier with two slits. When we do not measure which slit each particle goes through, they behave like waves, creating an interference pattern of stripes on a detector screen behind the slits, as if each particle went through both paths simultaneously. If we place a measuring device at the slits to catch each particle in the act, they behave like little bullets going through one slit or the other, and the interference pattern vanishes. The act of observation changes the outcome. Wheeler's genius was to ask, what if we delay that choice? What if we wait until after the particle has already passed through the slits and is on its way to the screen before we decide whether or not to measure its path? According to quantum mechanics, the particle should be in a superposition of having gone through both slits until it is observed. Wheeler proposed an apparatus where the decision to measure the which path information could be made randomly by a distant detector long after the particle's journey was seemingly complete. Astonishingly, experiments have confirmed this bizarre prediction. The results show that the choice made in the present, after the particle has already traversed the apparatus, determines whether it behaved as a wave or a particle in the past. It is as if the particle's history is not fixed until we look at it. The present observation retroactively decides what happened. This is not time travel in the classical sense, but a profound statement that the past is not a solid chain of events. It is a tapestry of possibilities that only becomes a single, definite history when it is observed in the present. Wheeler saw this as evidence for a participatory universe. The entire cosmic story, from the Big Bang to the formation of galaxies and life, might be a vast, self-excited circuit. The universe evolved in such a way as to produce conscious observers, and those observers, by the very act of perception, reach back and give definite form to the universe that led to their existence. It is a closed loop, a cosmos that begets life so that life can, in turn, beget the cosmos. This turns fine-tuning on its head. We are not lucky accidents in a hospitable universe. The universe is hospitable because, in some deep sense, it required us to become real. Our observation is the final piece that snaps the entire history into focus. This idea borders on the mystical, yet it emerges from the cold, hard mathematics of quantum theory. It suggests that reality is not a pre-recorded film we are watching, but a live performance being written moment to moment, with our conscious attention as the essential ingredient that makes the stage, the props, and the actors solid. We are not just the audience, we are the co-authors of the entire show. Yet this participatory role for consciousness, while elegant, leaves many physicists deeply unsettled. It seems to place a mystical veil over the machinery of reality. What if there is a way to remove the mystery entirely, to restore a clockwork universe where everything has a definite position and path, even at the quantum scale? This is the bold promise of pilot wave theory, also known as the de Broglie-Bohm theory, a deterministic alternative that has been revived from the fringes of physics. It dares to suggest that particles are not probability clouds, but real, tiny objects with precise locations at all times, guided by an invisible force. To see its power, we must return once more to the iconic double-slit experiment, but view it through a radically different lens. In the standard interpretation, a single electron fired at the two slits behaves as a wave of possibility, passing through both openings simultaneously and interfering with itself to create a striped pattern. It only becomes a particle at the moment of detection. Pilot wave theory rejects this duality. It says the electron is always a particle, a tiny speck with a definite trajectory. But it is not traveling alone. It is riding atop a real, physical wave that fills all of space, a guiding wave or pilot wave that dictates its path. This pilot wave passes through both slits, just like an ordinary wave in water. The particle itself, however, is a localized object, so it only goes through one slit or the other, like a cork bobbing on the water's surface. The magic is in the interaction. The pilot wave, having traveled through both slits, creates an interference pattern in its own structure. This pattern then guides the particle along a very specific, deterministic path, steering it to certain areas on the detector and avoiding others. The final result, after many particles are sent, is the familiar striped interference pattern. There is no collapse, no observer-created reality, and no probability fundamental to nature. The outcome is 100% determined by the initial conditions of the particle and its guiding wave. This provides a breathtakingly clear causal picture of quantum behavior. The famous fuzziness is not in the particles, but in our ignorance of the exact state of the hidden pilot wave. This theory elegantly eliminates the central paradox of quantum mechanics. There is no need for an observer to collapse anything because the particles were never in a superposition to begin with. They had real positions all along, simply hidden from our view. Schrödinger's cat is definitively alive or dead from the moment the box is sealed, its fate sealed by the precise configuration of its pilot wave. The universe, in this view, is perfectly deterministic. If you could know the exact position of every particle and the exact shape of the universal pilot wave, you could, in principle, calculate the entire future and past with perfect accuracy. This is a comforting, Newtonian vision of cosmic clockwork, yet this clarity comes at a profound and controversial cost. To work, the theory requires two deeply non-intuitive features. First, it is explicitly non-local. The pilot wave guiding a particle here and now can be instantaneously influenced by events happening arbitrarily far away. If you change the setup of the double-slit experiment on the other side of the galaxy, the pilot wave here changes instantly, altering the path of the particle. This violates the spirit, though not the letter, of Einstein's relativity, which states no information can travel faster than light. Second, it relies on what are called hidden variables, the precise positions of the particles that are, by the theory's own design, impossible for us to measure completely. The mainstream critique, solidified by John Bell's theorems, is that any such hidden variable theory must be non-local. For many physicists, accepting spooky action at a distance as a real, physical feature of a guiding wave is a higher price to pay than the probabilistic weirdness of the standard model. It trades one mystery for another, yet for its proponents, pilot wave theory offers something invaluable, a universe that is real, definite, and independent of whether anyone is looking. It is a stubborn, beautiful reminder that our most successful theory may still have a deeper, more intuitive story waiting to be told. A story where every particle has a secret map, and every strange quantum effect is just the visible wake of a hidden, guiding tide. Pilot wave theory restores a definite reality, but at the cost of accepting hidden, instantaneous connections. What if, instead of choosing between a fuzzy reality or a spooky one, the solid world we see emerges from a simple, physical process of information spreading? This is the core insight of quantum Darwinism, a theory that elegantly explains how the quantum realm of possibilities gives birth to our shared classical reality. It proposes that the transition is not a magical collapse, but a survival of the fittest, where the most robust quantum states are naturally selected by their environment. The problem it solves is profound. In the pristine isolation of a laboratory, particles can exist in superpositions, being in multiple states at once. Yet we never see a cat that is both alive and dead, or a table that is in two places simultaneously. Our macroscopic world is stubbornly definite. Quantum Darwinism argues this definiteness is not an illusion, but the result of a constant, relentless interaction. Every object, from a dust mote to a planet, is continuously bombarded by its environment. Photons of light bounce off it, air molecules collide with it, and even the faint hum of background radiation leaves a mark. Each of these interactions carries away a tiny bit of information about the object. Crucially, not all possible quantum states of the object are equally good at leaving these informational footprints. Think of a spinning coin. While it is in the air, it is in a superposition of heads and tails, but the moment it lands on a table, its state is imprinted onto the surface. The table does not record a fuzzy blend of heads and tails. It records one definite outcome because that is the stable state that can be consistently copied by the countless atoms in the wood grain. The head state or the tail state is robust, while the spinning superposition is fragile and instantly disrupted by contact. This process is called decoherence, and it is incredibly fast. For large objects, it happens in a fraction of a second, which is why we never perceive quantum weirdness at our scale. Quantum Darwinism takes this a step further. It says that among all possible quantum states, only a select few are fit enough to be widely copied and disseminated into the environment. These are the pointer states, the classical properties we are familiar with, like an object's position or its momentum. A single photon bouncing off a teacup does not just interact with one atom. It scatters off billions, imprinting the same information. The teacup is right here onto countless environmental fragments. This information proliferates, getting redundantly encoded in the photons, the air, the dust. You, as an observer, do not need to access some special hidden quantum layer. You simply intercept a tiny, random sample of this widely broadcast information. By looking at the light reflecting from the cup, you are tapping into a consensus reality that has already been established by the environment. The cup's position was selected not by your consciousness, but by its ability to survive and replicate its information in a noisy world. In this view, objective reality is not a single, absolute truth, but a robust, widely distributed consensus. It is what remains after the fragile quantum superpositions have been washed away by the relentless tide of interaction. We see the world as classical and definite because we are only ever privy to the information that was strong enough to be copied 1,000,000 times over. The quantum weirdness is still there, underlying everything, but it is hidden from our view, drowned out by the deafening chorus of redundant data proclaiming that the cup is on the table, the cat is alive, and the world is as solid as it seems. This theory bridges the quantum classical divide not with magic, but with a process as natural as erosion, where only the hardest stones of information withstand the constant weathering of the environment to shape the landscape of our perceived reality. Quantum Darwinism shows a reality sculpted by environmental consensus, but what if the transactions that build our world are not just happening around us, but also through time itself? This brings us to a theory that reframes every quantum event as a kind of cosmic negotiation, the transactional interpretation proposed by physicist John Cramer. It offers a breathtakingly symmetrical vision where the future and the past reach out to each other to settle the present. In this model, particles do not simply travel from point A to point B. Instead, every emission of energy, every photon leaving an atom, begins with an offer. The emitter sends out not one wave, but a wave that travels forward in time, an offer wave exploring all possible paths to potential receivers. This wave is a quantum proposal, a what-if. When this offer wave encounters a possible absorber, like an atom waiting to receive that energy, something remarkable happens. That absorber responds by sending its own wave backward in time, a confirmation wave retracing the exact path of the offer wave back to the source. It is a signal of acceptance. Only when these two waves, the forward-moving offer and the backward-moving confirmation, meet and reinforce each other does a transaction become complete. At that moment of handshake across time, energy is transferred, a particle is detected, and a definite event pops into reality. the probability of any given event is determined by the strength of this handshake. The most likely transactions are those where the offer and confirmation waves line up most powerfully, creating the peaks and valleys we interpret as probability distributions. This elegant dance explains quantum weirdness with startling clarity. Take the double-slit experiment once more. A single photon is emitted. Its offer wave travels forward, passing through both slits and creating an interference pattern of possibilities on the detector screen. Absorbers all across the screen send their confirmation waves back in time, but which transaction is completed? The one where the combined strength of the waves is greatest, which occurs at the bright bands of the interference pattern. The photon does not choose a path. The entire timeline from emission to absorption negotiates a single, consistent history. This framework makes sense of spooky action at a distance, quantum entanglement, in an even more radical way. When two particles become entangled, their offer and confirmation waves become linked across space and time. A measurement on one particle here and now completes a transaction that involves the other particle's waves, instantly determining its state, because the confirmation wave from the future measurement has already traveled back to the moment of entanglement to seal the deal. The strangeness is not in faster-than-light communication, but in a process that is fundamentally timeless, a single agreement woven through the entire history of the particles. Yet this beautiful symmetry comes with a profound and dizzying consequence: retrocausality. The theory requires that effects can precede their causes in a limited quantum sense. The confirmation wave from a future absorption event is a necessary part of causing the emission event in the past to become real. It is a closed loop where the future helps to create the past that leads to it. This does not mean you can send a message to your younger self, as these handshakes are constrained by quantum probabilities and cannot carry arbitrary information. But it does suggest that the flow of time as a one-way street is an illusion at the quantum level. Reality may be settled by a kind of democratic vote across past, present, and future, where an event is not real until all moments agree it happened. The universe, in this view, is a vast network of settled deals, each one a shimmering thread in the fabric of spacetime, woven from both ends simultaneously. We experience only the outcome, the moment the handshake is firm, never seeing the whispers of offer and confirmation that reached through time to make our now a certainty. But if the strings of string theory offer one path to a deeper reality, there exists another, profoundly different vision that seeks to mend the greatest fracture in modern physics. Loop quantum gravity is a bold, elegant framework that asks a radical question. What if we do not need extra dimensions or vibrating strings to unify the cosmos? What if instead we must rebuild the very stage upon which the drama of particles plays out, the fabric of space and time itself? This theory does not seek to quantize matter within space, but to quantize space and time right down to its most fundamental essence. The central idea is breathtaking in its simplicity. In our everyday experience, space seems smooth and continuous. You can always imagine dividing a meter into smaller and smaller parts forever. Loop quantum gravity declares this is an illusion. Just as matter is made of discrete atoms, space itself is woven from tiny, indivisible threads of reality. Picture the universe not as a blank canvas, but as an incredibly fine, dynamic mesh, a network of interwoven loops. These are not loops in space, they are the very fabric of space. Where these loops intersect, they create nodes, and the entire network vibrates and evolves, defining the geometry of the cosmos. In this view, there is no such thing as empty space. There is only this vibrant quantum tapestry of connections. This granular nature of space has a stunning and testable consequence. It provides a definitive answer to one of cosmology's most troubling puzzles, the Big Bang singularity. In Einstein's general relativity, if you rewind the expansion of the universe, you are forced to a point of infinite density and curvature, a place where the laws of physics break down completely. It is a mathematical warning sign that our theory is incomplete. Loop quantum gravity smooths out this infinity. Because space itself is quantized, there is a smallest possible volume, a quantum of space. You cannot squeeze the universe into a point smaller than this fundamental grain. So what happens when you rewind the cosmic film? Instead of a catastrophic singularity, the theory predicts a quantum bounce. The immense gravitational squeeze of a collapsing universe reaches a point of maximum density, and then, repelled by the quantum nature of spacetime itself, it rebounds. Expansion begins anew. This single prediction opens a door to a cosmos of staggering possibility. Our Big Bang may not have been a beginning from nothing, but a transition, a moment of rebirth. It could have been the bounce point from a previous universe that had contracted down to that quantum limit. This suggests a cyclic model of existence, a cosmos that breathes, expanding and contracting over eons, each cycle lasting perhaps trillions of years. Our entire universe, with all its galaxies and history, would be just one phase in an endless cosmic heartbeat. In each cycle, the physics might be subtly reshuffled, leading to a new universe with different constants and possibilities. We would be living in the aftermath of one bounce, destined perhaps in the far, far future to become the prelude to another. The implications reach into the heart of time itself. If space is granular, then time must also be discrete. There is a smallest possible tick of the cosmic clock, a quantum of time. Our smooth, flowing experience of seconds and hours would be an emergent property, like the smooth motion of a movie emerging from a sequence of still frames. At the most fundamental level, the universe might not change continuously, but in tiny, discrete jumps. This vision offers a universe that is profoundly interconnected and finite in its building blocks, yet potentially infinite in its duration. A timeless dance of space loops cycling through phases of creation, not from a mysterious singularity, but from its own resilient quantum structure. The granular universe of loop quantum gravity offers a vision of rebirth from a quantum bounce, but there exists another, even more visceral image of cosmic origins. Our entire universe, with all its galaxies and swirling nebulae, might not be expanding into a void, but falling into a bottomless pit. This is the startling premise of black hole cosmology, a theory that proposes we are living inside a black hole. In this view, the Big Bang was not the beginning of everything, but the violent birth of a new reality within the crushing depths of a singularity from a parent universe. The parallels are eerily compelling. Consider what happens when a massive star collapses. Its core condenses into a point of infinite density, a singularity shrouded by an event horizon, a spherical boundary from which not even light can escape. Now rewind our own cosmic history. The standard Big Bang model also begins with a singularity, a point of infinite density from which all space, time, and matter erupted. Could these two singularities be the same phenomenon, seen from different sides? From the outside, a black hole is a trap, but from the inside, its geometry is not a static prison. The mathematics of a black hole's interior, as described by Einstein's equations, reveal a space that is not still but violently dynamic. For anything that crosses the event horizon, all paths lead inexorably toward the central singularity. Space itself flows inward like a river rushing toward a waterfall. Now flip the perspective. What if that inward rush is what we, from our vantage point inside, perceive as the outward expansion of the universe? The relentless pull toward the singularity in the future of the black hole becomes the explosive rush from a singularity in our past. Our cosmic expansion could be the gravitational free fall of an entire reality. This idea creates a staggering fractal genealogy of existence. Every black hole that forms in a parent universe could, in its interior, harbor the seeds of a new cosmos with its own spacetime, physical laws, and potentially its own stars and life. Our universe, with its hundreds of billions of galaxies, each containing billions of stars, would itself be a stellar nursery for new realities. Every star that collapses into a black hole within our cosmos may not be an end, but a gateway, birthing a daughter universe in its infinitely dense heart. We could be part of an infinite chain, a cosmic matryoshka doll of realities nested within realities. The properties we observe fit this strange picture surprisingly well. The uniformity of the cosmic microwave background, the faint afterglow of the Big Bang, could be explained as the thermal radiation from the event horizon of our parent black hole, stretched and diluted over eons. Even dark energy, the mysterious force accelerating cosmic expansion, might find an explanation as the tidal forces of our continued fall. This theory reframes the ultimate fate of our cosmos. If we are inside a black hole, then the long-term future may not be an eternal cold thinning, but a final, catastrophic merger with the central singularity. Yet even that ending could be a new beginning, perhaps triggering another bounce or birthing another layer of reality in an endless cycle of creation within destruction. It suggests a cosmos where death and birth are not opposites, but two faces of the same profound transformation, where every ending is simply the horizon of a new story. Black holes offer one vision of a universe born from destruction, but there is a theory that finds creation in a different kind of cosmic violence. The ekpyrotic universe proposes our entire reality was born not from a singular point, but from a shattering collision in a higher dimensional realm. This radical idea emerges from the mathematics of string theory, but it paints a very different picture of the beginning. It suggests that the three-dimensional space we inhabit is not all there is. It is a membrane, or brain for short, a vast, flexible sheet floating within a higher dimensional expanse called the bulk. Our universe is not alone on this stage. There exists another brain, a parallel world of its own, hovering silently in the bulk, separated by a tiny gap. In the ekpyrotic model, the Big Bang was not an explosion from nothing. It was the moment these two colossal membranes, moving through the bulk, finally touched. The kinetic energy of their collision was so immense, so focused, that it flooded our brain with the searing heat and radiation that became the primordial soup of our cosmos. Imagine two sheets of paper floating parallel in a quiet room. Now imagine them slowly drifting toward each other until they meet. The moment of contact sends a ripple of energy across their entire surface. That ripple on a cosmic scale is our expanding universe. This leads to an even more profound possibility, a cyclic model. After the collision, the brains bounce apart, propelled by the energy of the impact. They then drift through the bulk, slowly losing momentum, until gravity from the bulk itself pulls them back together for another cataclysmic encounter. Each collision resets the cosmic clock, triggering a new Big Bang and a new cycle of expansion, cooling, and structure formation. Our universe is just one episode in an endless series, a cosmic heartbeat that has been ticking for eternity, with no true beginning and no final end. This stands in stark contrast to the theory of cosmic inflation. Inflation proposes a single, ultra-rapid expansion that smoothed and flattened our universe from a microscopic seed. The ekpyrotic model achieves a similar smoothness and flatness not through a brief, violent stretch, but through a long, slow contraction of the brains before they collide. This slow squeezing smooths out wrinkles and irregularities, preparing a pristine slate for the next bang. The key difference lies in their predictions for the faintest echoes of creation, primordial gravitational waves. Inflation's hyper-accelerated expansion should have shaken spacetime itself, generating a strong background hum of these waves that might be detectable in the polarization of the cosmic microwave background. The ekpyrotic scenario, with its slower, gentler prelude, predicts a much quieter signal. Our search for these ancient ripples is not just a technical challenge, it is a direct listen into the mechanism of our origin. Finding them, or definitively not finding them, could tell us whether our universe was born from a solitary, inflationary shout, or from the timeless, rhythmic crash of worlds we can never see. The rhythmic crash of colliding worlds offers a grand, physical origin story, but there is a theory that strips reality down to its most fundamental essence, not as matter or energy, but as pure information. This is the vision of digital physics, which argues the universe is not just like a computer simulation. It is a computer running a computational process at the very smallest scales of existence. In this view, the cosmos is not built from tiny strings or loops, but from bits, the ones and zeros of a cosmic program being executed at the Planck scale, the absolute limit of how small anything can be. The laws of physics are not mysterious forces, but the algorithms of this ultimate computation. One of the most compelling frameworks for this idea comes from the work of Stephen Wolfram and his physics project. He explores the possibility that the complex behavior of our entire universe emerges from incredibly simple rules, much like a cellular automaton. Imagine a vast, infinite grid, like a chessboard that stretches forever. Each square or cell can be in one of a few states, say black or white. Now, apply a simple rule that determines each cell's next state based on the states of its immediate neighbors. For example, a rule might say, a cell becomes black if exactly two of its neighbors are black, otherwise it becomes white. You set an initial pattern, apply the rule to every cell simultaneously, and then watch the grid evolve step by step. From these mind-numbingly simple beginnings, astonishing complexity can arise. Certain rules produce patterns that grow, change, and interact in ways that look organic, almost lifelike, creating structures that move, replicate, and compute. Wolfram's radical suggestion is that our universe operates on a similar principle. The underlying substrate of reality might be a hypergraph, a network of abstract points and connections, updating according to simple, deterministic rules at the Planck scale of time, about 10 to the negative 43 seconds. From this ceaseless, low-level computation, everything we perceive emerges. Spacetime itself is not a smooth continuum, but a coarse-grained picture of this evolving network. The three dimensions we move through, the flow of time, even the force of gravity, could all be collective illusions, emergent phenomena arising from the statistical behavior of countless discrete computational events. Particles like electrons and quarks would not be little balls, but persistent, stable patterns in this cosmic computation, like gliders or oscillators in a cellular automaton, moving and interacting according to the deeper rules. This reframes the mystery of quantum mechanics. The famous probabilistic nature of particles could be a consequence of our limited, macroscopic view. We are like someone watching a detailed movie on a screen with extremely low resolution. We see a blurry, pixelated image where definite details seem to flicker in and out of existence, appearing probabilistic, while at the fundamental, high-resolution level, every pixel state is perfectly determined by the rule. The weirdness of superposition and entanglement might be artifacts of our perspective, not fundamental truths. This digital universe is deterministic, yet it can generate the appearance of free will and true novelty, just as a complex computer program can produce outcomes that are unpredictable to anyone but the machine itself. It suggests a cosmos that is, at its heart, a vast, ongoing calculation, where every star, every thought, every law of nature is a magnificent, emergent pattern in the cosmic code. We are not just living in a simulation, we are the transient, beautiful output of a universe that is computing itself into existence, one Planck-sized step at a time. This digital universe computes its own reality, but what if the very stage it computes upon is itself an elaborate illusion? Cognitive scientist Donald Hoffman proposes a theory so radical it challenges the foundation of all our scientific inquiry. He argues that space-time, matter, and physical objects are not fundamental features of reality. They are not the hardware of the cosmos. Instead, they are a user interface, a simplified desktop projected by our own consciousness to help us navigate a world that is far stranger and more complex than we can perceive. To grasp this, think of the computer screen in front of you. You see icons for folders, files, and a trash can. You interact with them by clicking and dragging. But you know that these colorful icons are not the reality of the computer. The true reality is the unimaginably complex world of silicon circuits, electrical voltages, and binary code running beneath the surface. The desktop is a brilliant simplification, a user-friendly interface designed to hide the overwhelming complexity of the machine, so you can get things done without needing a degree in electrical engineering. Hoffman suggests our perception of reality works in exactly the same way. The apple you see is not a fundamental object, it is an icon. The three-dimensional space it sits in is not a fundamental container. It is the desktop. The laws of physics are not the ultimate rules of the universe. They are the operating system of the interface, the consistent rules for how the icons behave. This interface exists for one crucial evolutionary reason: fitness, not truth. Our senses did not evolve to show us reality as it truly is. They evolved to give us a survival advantage. Showing us the true, underlying reality, whatever that may be, would be like showing a computer user the raw machine code. It would be confusing, paralyzing, and utterly useless for finding food, avoiding predators, and finding a mate. So evolution built a virtual reality headset for each species tailored to its needs. A fly sees a very different desktop with different icons than we do, because that is what helps a fly survive. None of us are seeing what is really there. We are all interacting with a convenient fiction. So what lies behind the icons? Hoffman proposes that the fundamental reality is a vast network of conscious agents. These are not human minds, but the most basic building blocks of existence, entities that have some form of experience and can make decisions. In his view, consciousness is not a late-arriving product of complex brains. It is the primary substance of reality. Physical objects, from atoms to galaxies, are merely the symbols that conscious agents, like you and me, use to communicate with each other within the shared interface. The apple is not a collection of atoms. It is a data structure in the perceptual interface that represents something about the interactions of conscious agents in the deeper reality. This turns all of science on its head. Physics is not the study of fundamental reality. It is the study of the user interface rules. It is like reverse engineering the software of a video game without ever having access to the computer it runs on. We are magnificent cartographers, meticulously mapping the desktop while remaining completely blind to the circuitry beneath. The theory makes startling predictions. It suggests that if we could somehow peek behind the perceptual veil, the concepts of space, time, and objects would dissolve into something completely alien, a realm of pure consciousness and mathematical relationships that our brains are simply not wired to visualize. This explains the profound weirdness of quantum mechanics, the famous observer effect where particles seem to behave differently when measured. Might not be about physical disturbance, but about the act of a conscious agent accessing an icon in the interface, which triggers a change in the data structure. Entanglement, where particles remain connected across vast distances, could be a reflection of a deeper, non-spatial connection between conscious agents in the foundational network. Hoffman's conscious realism is not a retreat into mysticism, but a bold scientific hypothesis framed with mathematical rigor. It asks us to consider that everything we have ever known, the solid ground beneath our feet, the vast expanse of the cosmos, the very screen you are looking at now, is a magnificent collaborative hallucination. Our reality is a shared dream, a desktop simulation running on the hardware of a consciousness so profound and ancient, we have forgotten we are the programmers, endlessly clicking on icons of our own creation, mistaking the symbol for the source code of existence itself. Our shared desktop of reality assumes time flows in one direction, but at the quantum level, the code might be running in both directions at once. The two-state vector formalism is a theory that boldly challenges the arrow of time, proposing that a quantum particle's present is not shaped solely by its past but equally by its future. In this view, the complete description of a particle at any moment requires two states, not one. There is the usual forward evolving state determined by how it was prepared in the past. But there is also a backward evolving state determined by how it will be measured in the future. The particle's actual behavior is a handshake between these two waves of influence, one from yesterday and one from tomorrow. This is not science fiction, but a rigorous mathematical framework that makes precise, testable predictions. To test such a bizarre idea, physicists needed a way to gently probe a quantum system without fully collapsing it. This led to the development of weak measurement. Unlike a standard, strong measurement that forces a particle to pick a definite property, a weak measurement is a mere whisper. It extracts just a tiny bit of information by coupling the particle very gently to a measuring device. The trade-off is that any single weak measurement is incredibly noisy and uncertain. But by repeating the experiment thousands of times and averaging the results, a startling signal can emerge from the noise, the weak value. Experiments using this technique have revealed phenomena that seem to defy common sense. In one famous setup, photons were sent through an interferometer, a device that lets them travel multiple paths. By using weak measurements, researchers were able to infer where the photons were, on average, between their starting point and their final detection. The results were astonishing. The data suggested that before they were detected, the photons had taken paths that were, on average, outside the allowed regions of the apparatus. It was as if their trajectory was guided not just by where they came from, but by where they were destined to end up. The future measurement choice seemed to be reaching back to sculpt the particle's journey. This is the essence of the two-state vector, a present moment negotiated between past preparation and future outcome. The implications for retrocausality are profound. It suggests that influence from the future is not a logical impossibility, but a feature of quantum mechanics we have simply ignored. Causes can indeed precede effects, but in a subtle, statistical way that does not allow for paradoxes like sending a message to your past self. The future boundary condition acts as a constraint, making some histories more likely than others. This directly challenges our deepest intuitions about free will. If the future is already playing a role in shaping the present, does that mean our choices are predetermined? Not necessarily. In this framework, free will might not be about creating a future from nothing, but about our conscious experience being the process of navigating a landscape of possibilities whose boundaries are set by both the past we remember and a future that is, in some sense, already written. Our decisions feel real and agonizing because we are the point where these two waves of time meet and crystallize into a single, lived moment. We are not just beings moving forward through time, we are the dynamic intersection where all of time, from beginning to end, converges to create the now. The strange handshake between past and future suggests time is more fluid than we feel. But what if the entire quantum framework is not a description of the world but a guide for navigating it? This is the provocative core of quantum Bayesianism, or QBISM, an interpretation that dissolves the paradox of the observer by making probability deeply, undeniably personal. QBISM argues that the probabilities at the heart of quantum mechanics are not statements about an objective, hidden reality. They are not features of the universe itself. Instead, they are subjective degrees of belief, a personal betting odds assigned by an individual agent based on their unique history of interactions with the world. In this view, quantum mechanics is not a theory of what is, but a theory of what to expect. It is a user's manual for an uncertain reality, written from the first-person perspective. To understand this, think of a weather forecast. When a meteorologist says there is a 70% chance of rain tomorrow, she is not describing an objective, pre-existing fact about the atmosphere. The atmosphere is in a single, definite state, but it is so complex that our best knowledge only allows us to assign a personal probability. That 70% is a measure of the forecaster's confidence, shaped by data from satellites, models, and past experience. It is a belief, not a reality. QBISM treats quantum probabilities in exactly the same way. When a physicist says an electron has a 50-50 chance of spinning up or down, she is not describing a particle in a superposition. She is expressing her own informed uncertainty, her personal betting odds for what will happen when she performs a specific experiment. The electron itself is not in two states at once. It simply has properties that are, for all practical purposes, unknown until a specific interaction forces them into the open. This radically reshapes the role of the observer, or as QBISM prefers, the agent. An agent is any entity that can take actions, make measurements, and update its beliefs. You are an agent. A cat could be an agent. Even a sophisticated robot might qualify. Each agent builds their own quantum universe, a private landscape of expectations based solely on their own history of interactions. My quantum state for a system is not the same as yours because my experiences, my measurements, and my background knowledge are different. We only find common ground when we compare notes, communicate our results, and update our personal probability tables to align. This creates a profoundly personal kind of multiverse. It is not an infinity of branching, physically real worlds. It is a multiverse of potential experiences, a probabilistic landscape that exists uniquely within the belief system of each conscious agent. Before you open the box, your personal quantum state for Schrödinger's cat includes strong probabilities for both a living and a dead cat. These are not two real cats in two real universes. They are two potent possibilities in your own mental model of the situation. The moment you look, you have a new experience, you update your beliefs with certainty, and your personal multiverse of possibilities collapses into a single, definite memory. The cat was always definitively one or the other, but you did not know which, and quantum mechanics was the calculus you used to manage your ignorance. This elegantly sidesteps the measurement problem. There is no mysterious collapse of a wave function because the wave function was never a physical thing. It was always just a list of an agent's probabilities, a tool that becomes obsolete the moment new data arrives. Entanglement is not spooky action at a distance, but a correlation between the personal belief systems of agents who have shared a history of interaction. It reflects a harmony of expectations, not an invisible thread through space. QBISM offers a universe that is solid, singular, and independent, but one that reveals itself in pieces through the lens of individual experience. We are not passive observers of a quantum drama, nor are we creators of reality. We are gamblers in a casino of existence, each of us holding our own private betting slip, constantly refining our odds as we place our chips on the next turn of the cosmic wheel. The multiverse is not out there. It is the shimmering map of maybes and might best that you carry in your mind, a personal guide to navigating a world that forever keeps its final cards close to its chest. But if our minds are the private bookmakers of reality, where do the bets themselves originate? The very nature of consciousness remains the deepest mystery, a ghost in the machine of our quantum theories. Two renowned thinkers, physicist Roger Penrose and anesthesiologist Stuart Hameroff, have proposed a radical bridge between these realms. Their orchestrated objective reduction theory, or OR, suggests consciousness is not an emergent property of classical brain chemistry, but a quantum process happening within the very fabric of our neurons. At the heart of every neuron in your brain are structures called microtubules, tiny cylindrical scaffolds that give the cell its shape and help transport materials. Hameroff proposed these are not just passive pipes. Their intricate lattice-like structure could support long-lasting quantum coherence, a state where particles within them can exist in superposition, performing multiple computations at once. This is where Penrose's contribution becomes revolutionary. He argued that the wave function collapses we have discussed, the moments when quantum possibilities snap into a single reality, are not random or triggered by any ordinary interaction. They are objective reductions, events driven by the subtle, accumulating influence of gravity. When the superpositioned states within the microtubules reach a certain threshold of mass-energy difference, their own tiny spacetime geometries become unstable, forcing a spontaneous collapse. This collapse is not a calculation. Penrose believes it is a non-computable process, a moment where physics touches something beyond algorithmic processing, perhaps the bedrock of Platonic mathematical truth. According to OR, each of these orchestrated collapses is a moment of proto-consciousness, a flicker of experience. The symphony of billions of these events across the brain's neural networks, orchestrated by biological structures, gives rise to our rich, unified stream of awareness. Your sense of self, your qualia of the color red or the taste of chocolate, is not a byproduct of firing neurons, but the intrinsic feeling of these quantum gravitational collapses happening within you. This theory makes a breathtaking connection to the nature of reality itself. It implies that consciousness is not a passive observer of a predetermined quantum world. It is an active participant, intimately linked to the very mechanism that resolves quantum possibilities into actuality. In this view, your mind is not just reading the cosmic code, it is executing a fundamental step in its processing. The collapse that creates a definite reality and the flicker of conscious experience may be two sides of the same coin. This idea is fiercely controversial. Critics point out that the warm, wet, noisy environment of the brain seems utterly hostile to delicate quantum states, which typically require extreme cold and isolation to persist. They argue classical neuroscience explains cognition adequately without invoking quantum magic. Yet OR persists, a daring synthesis that refuses to separate the observer from the observed. It paints a picture where our innermost experience is woven from the same threads that stitch together reality, suggesting that to understand the universe, we may first need to understand how the universe understands itself through us. The ghost in the quantum machine may not be a ghost at all, but a deeper, hidden wholeness. Physicist David Bohm, troubled by the fragmented view of reality offered by standard quantum theory, proposed a radical alternative that saw the universe not as a collection of separate parts, but as an undivided whole. He called this vision the implicate order. Think of reality as having two layers. The world we perceive with our senses, the world of separate objects, definite locations, and linear time, is what Bohm termed the explicate order. It is the unfolded, manifest reality, like the ripples and waves on the surface of a pond. But beneath this surface, Bohm argued, lies a far more fundamental realm, the implicate order. Here, everything that appears separate and distinct in our world is deeply and inseparably enfolded together. In this hidden dimension, past, present, and future, here and there, are all present simultaneously, woven into a single, seamless fabric. To grasp this, Bohm used the powerful analogy of a hologram. Recall that in a hologram, every fragment of the film contains the information of the entire three-dimensional image. If you break a holographic plate into pieces, each shard, when illuminated, will still project the full picture, albeit with lower resolution. The whole is enfolded into every part. Bohm suggested our universe operates on exactly this principle. Every electron, every galaxy, every conscious thought is not an isolated entity, but a manifestation of the total cosmic order, unfolded into our explicate reality from the implicate background. The particle you see here is not fundamentally separate from the particle across the universe. They are both different expressions of the same underlying wholeness, momentarily unfolded in a way that makes them appear distinct. This provides a breathtakingly elegant framework for quantum non-locality, the spooky connection of entangled particles. In Bohm's view, when two particles become entangled, they are not sending signals faster than light. Instead, their separation is an illusion of the explicate order. In the deeper implicate reality, they were never truly separate to begin with. Their correlated behavior is simply the natural expression of their fundamental unity, becoming apparent when we force them to manifest in our unfolded world of measurement. The universe, then, is a constant process of unfolding and enfolding. The implicate order continuously gives rise to the explicate world of our experience, and the events of our world then fold back into the implicate whole, influencing future unfoldings. This dynamic flow suggests that time itself, as a linear sequence, is a feature of the explicate order. In the implicate realm, all of history and potentiality coexist. Our conscious experience is like a spotlight moving across this eternal tapestry, illuminating one thread of the pattern at a time and calling it the present. Bohm's vision is profoundly holistic. It dissolves the paradox of the observer and the observed because both are unfoldings from the same source. Our quest to understand the universe is not us as separate beings studying an external cosmos. It is the cosmos through the vehicle of our consciousness, unfolding an understanding of its own hidden, implicate nature. In this view, the strange connections, the probabilities, and the unity we glimpse in quantum mechanics are not bugs in reality's code, but faint echoes of a deeper, more connected truth, whispering that every fragment we see contains, in some mysterious way, the blueprint of the whole. Bohm's vision of an enfolded universe offers profound unity, but it collides with one of modern physics' most ferocious paradoxes, a battle of laws that threatens to tear apart the very fabric of spacetime at the edge of a black hole. This is the black hole information paradox, and its proposed resolution is so violent it suggests the edge of a black hole might be a wall of pure fire. The conflict is between two pillars of physics. Quantum mechanics, the rulebook for the very small, is built on a sacred principle, unitarity. This simply means information is never truly destroyed. If you burn a book, the ash and smoke seem to erase its story, but in principle, a being with perfect knowledge could reverse the process, gathering every particle and photon to reconstruct every word. Information is scrambled, not lost. General relativity, Einstein's theory of gravity governing the very large, paints a different picture for black holes. It describes a black hole with heartbreaking simplicity, defined only by its mass, spin, and charge. If you throw a grand piano, a secret diary, or a hard drive packed with data into a black hole, the black hole doesn't care. It just gets a tiny bit more massive. According to relativity, all the intricate information about those objects is utterly, permanently lost behind the event horizon, crushed into the singularity. For decades, physicists hoped Stephen Hawking's discovery of radiation offered a way out. Hawking showed that black holes are not perfectly black. Due to quantum effects at the event horizon, they slowly evaporate, emitting a faint glow of particles now called Hawking radiation. The problem is, this radiation is purely thermal, like the heat from a stove. It carries no information about what fell in. So, as the black hole evaporates completely over eons, all the information about the piano, the diary, and the hard drive seems to vanish from the universe forever. This violates quantum mechanics' core tenet. It is a paradox that cannot stand. Desperate for a solution, physicists explored a terrifying possibility. What if the event horizon is not the smooth, uneventful gateway relativity predicts? In 2012, a group of researchers proposed a shocking alternative, the firewall. They argued that to preserve information, the principle of unitarity demands a radical break from Einstein's gentle picture. Instead of an invisible boundary you could cross without noticing, the event horizon must be a seething, violent wall of ultra-high energy particles. An astronaut falling toward a black hole would not experience empty space. She would be incinerated, atomized by this firewall long before reaching the horizon. The firewall is born from a quantum contradiction. For information to escape in the Hawking radiation, the particles just outside the horizon must be quantum entangled with particles deep inside the black hole. But for an infalling astronaut to experience nothing unusual, as relativity insists she must, those same outside particles must also be entangled with the radiation that has already left the black hole. In quantum mechanics, a particle cannot be fully entangled with two different systems at once, a rule called monogamy of entanglement. Something has to give. The firewall hypothesis says the entanglement with the interior must violently sever the moment before crossing. That severance releases an astronomical amount of energy, creating the firewall. It is a brutal solution, saving information by sacrificing the peaceful continuity of spacetime. The implications are revolutionary. Accepting firewalls means Einstein's equivalence principle, the idea that free fall feels like floating in empty space, fails catastrophically at the most important boundary in the universe. It suggests that spacetime as a smooth continuum is not fundamental. It is an emergent approximation that shatters under extreme conditions, revealing a more basic, possibly discrete quantum structure of reality. The paradox forces us to choose which law is more sacred, the preservation of information or the smooth geometry of gravity. Resolving it may require a theory of quantum gravity, a framework that seamlessly blends the two, showing how information is neither lost nor trapped, but perhaps encoded in ways we cannot yet imagine, written onto the horizon itself or threaded through the fabric of a holographic universe. The firewall is not necessarily the final answer, but a glaring signpost that we are on the brink of a revolution, one that will redefine what happens at the edge of nothing and in doing so reveal what everything truly is. The searing violence of a firewall is one desperate answer, but there exists a far more elegant and beautiful possibility. Entanglement, that spooky link between distant particles, may not be a ghostly connection at all. It might have a physical shape, a secret tunnel through the fabric of reality itself. This is the stunning conjecture known as ER equals EPR, an idea that braids together the two greatest threads in 20th century physics. On one side, we have EPR, named for Einstein, Podolsky, and Rosen, the trio who first highlighted the bizarre, non-local link of quantum entanglement. On the other, ER, the Einstein-Rosen bridge, the formal name for a wormhole, a hypothetical shortcut through spacetime. The conjecture, advanced by physicists like Juan Maldaisner and Leonard Susskind, proposes a breathtaking equivalence. These are not two different phenomena. They are the same thing described in two different languages. Quantum entanglement between two particles is, in a precise mathematical sense, equivalent to a microscopic wormhole connecting them. Think of two entangled electrons, one here on Earth, another on a planet orbiting a distant star. According to standard quantum mechanics, measuring one instantly determines the state of the other, no matter the light years between them. Einstein famously called this spooky action at a distance. The ER equals EPR conjecture offers a geometric picture that banishes the spookiness. It suggests that if we could peer into the deepest architecture of spacetime at the quantum level, we would see that these two electrons are not truly separate. A Planck-scale wormhole, an Einstein-Rosen bridge, threads between them. This tunnel is not a traversable highway for matter or signals. It is a geometric connection, a stitch in the fabric of reality that makes the 2 points intimately close in a higher dimensional sense. The act of measurement here does not send a signal racing to its partner. Instead, it reveals a property that was always shared because the two particles are, in this geometric view, different mouths of the same underlying structure. This reframes entanglement not as a mysterious force, but as a symptom of spacetime's hidden connectivity. It provides a potential geometric foundation for the entire edifice of quantum mechanics. The probabilities and superpositions that seem so abstract could be shadows cast by a complex, woven geometry of microscopic wormholes linking every particle to every other in a vast dynamic network. Our classical experience of separate objects in smooth space would then be a coarse-grained illusion, like seeing a solid piece of cloth from a distance, unaware it is actually a tapestry of a trillion tiny threads. The implications for a theory of quantum gravity are profound. Gravity, in Einstein's vision, is the curvature of spacetime. Quantum mechanics governs the behavior of particles within that spacetime. Unifying them has been physics' greatest challenge because their mathematical languages seem incompatible. But if entanglement, a purely quantum phenomenon, is literally made of spacetime geometry, then the two theories are not separate. They are two perspectives on a single, deeper reality. The wormholes or Einstein-Rosen bridges are the geometric manifestations of quantum links. In this picture, to understand gravity at the quantum scale is to understand the network of entanglement that literally holds spacetime together. Sever enough of these quantum threads and spacetime itself might unravel or reconfigure. This leads to a radical view of black holes, the ultimate gravity engines. The conjecture suggests that the entanglement between particles hawking radiation emitted long ago and the quantum states deep inside the black hole is not just a correlation. It is a physical wormhole connection. As the black hole evaporates, this network of wormholes might somehow preserve the information, weaving it into the radiation in a way that avoids the need for a destructive firewall. The interior of the black hole and the distant radiation remain geometrically connected, ensuring no information is ever truly lost. It is a vision of a universe that is not empty space dotted with objects, but a living, dynamic quantum network, a cosmic neural web where every connection is a thread of spacetime, and every particle is a node in a graph of existence. We perceive distance and separation, but at the fundamental level, everything may be just a handshake away through a labyrinth of bridges too small to see. A hidden geometry where the spookiest thing about action at a distance is that there was never any distance to begin with. This hidden geometry of connections weaves a cosmos of breathtaking unity, yet it also opens a door to a form of repetition so vast it becomes a kind of immortality. There is an ancient philosophical idea contemplated by thinkers from the Stoics to Nietzsche that all of existence repeats in an endless cycle. The universe expands, collapses, and begins again, and in each new iteration, every event, every life plays out exactly the same. This concept of eternal recurrence feels like myth, a poetic metaphor, but when we place it beside the quantum multiverse and the nature of infinity, it transforms from philosophy into a startling physical possibility. In a cosmos that is either infinite in space or eternal in time, or both, the dice of reality are thrown not just once, but an infinite number of times. An infinity plays by rules that defy our finite intuition. Consider a simple analogy: a deck of cards. Shuffle a standard deck thoroughly. The specific order of the 52 cards is one arrangement among an astronomically large number of possibilities. But if you had an infinite amount of time to shuffle, you would not only eventually repeat that first order, you would repeat it an infinite number of times. Now scale this up to the universe. Our reality, at its most fundamental quantum level, can be thought of as a configuration of a finite number of particles in a finite volume of space, each with a finite set of possible quantum states. Even though the number of possible configurations is unimaginably huge, it is still, in principle, finite. If the universe is truly eternal, or if the multiverse contains an infinite number of separate cosmic bubbles, then this finite set of possible arrangements must repeat. This leads to a conclusion that is both comforting and deeply unsettling. Somewhere in another cosmic bubble or in another cycle of time trillions of years from now, there exists a galaxy identical to our Milky Way. Orbiting a star identical to our Sun is a planet identical to Earth. On that planet, a person identical to you in every quantum detail is reading these very words, having lived a life indistinguishable from your own up to this exact second. And this is not a one-time coincidence. In an infinite ensemble, this perfect match does not happen just once. it happens an infinite number of times. Every joy you have ever felt, every moment of sorrow, every mundane choice of what to have for breakfast has already happened countless times before and will happen countless times again, in realms forever separated by unimaginable reaches of space or time. The quantum nature of reality adds a haunting layer to this. In the many worlds interpretation, every decision creates a new branch. But in an eternal or infinite multiverse, even those branching histories are not unique. There are not just branches where you turned left and branches where you turned right. There are entire, separate cosmic arenas where the branching pattern itself is identical, producing a copy of you who experienced the exact same sequence of choices and outcomes. Your entire timeline, with all its quantum randomness resolved in precisely the same way, is being lived out in duplicate, like a book printed in infinite editions across an endless library. This idea dissolves the very concept of uniqueness. The atoms that make up your body are common. The patterns of your thoughts, as complex as they are, arise from the laws of physics and chemistry. In an infinite playground, any pattern that can exist and must exist again and again. There is no original you. There is only a template, a specific arrangement of information recurring endlessly throughout the metacosmos. Your consciousness, that feeling of being a singular self, may simply be the local perspective of one instance of that template, unaware of its countless echoes. This form of recurrence is not a predetermined fate, as in the philosophical version. It is a statistical inevitability. It does not mean you are doomed to repeat the same life. It means that among the infinite variations, the exact pattern of your life is out there, an infinite number of times. Other versions of you live every possible variation, but an infinity of others live this one. So the next time you experience a moment of profound beauty or a flash of déjà vu, consider a possibility that transcends poetry. You are not just living this moment. You are reliving a moment that is, in the grand architecture of eternity, a permanent fixture of reality, playing on a loop in the cosmic background forever. This endless recurrence of self suggests a reality that is deeply interconnected, perhaps even dependent on being seen. But what if observation does more than just reveal reality? What if it actively preserves it? This brings us to a bizarre and counterintuitive quantum phenomenon with profound philosophical implications, the quantum Zeno effect. Named after the ancient Greek philosopher Zeno of Elea, who proposed paradoxes about motion being an illusion, this effect reveals that watching something very, very closely can actually stop it from changing. In the quantum realm, an unstable particle, like a radioactive atom, has a certain probability of decaying within a given time. Left unobserved, it will eventually decay. But if you rapidly and repeatedly measure it, asking over and over again, "Are you still in your initial state?" something strange happens. The frequent acts of observation reset the quantum clock, effectively pinning the particle in its original, undecayed condition. It is as if the universe, caught in the act of trying to change, is forced to snap back to its starting point every time we look. The mechanism is tied to the wave function collapse we have discussed. Each measurement forces the system to declare its state. For that brief instant, its probability of being in the initial state becomes 100%. If measurements come in rapid succession, the system barely has time to evolve into a state where decay is probable before it is reset again. Over time, the chance of it ever slipping through to the decayed state becomes vanishingly small. The system is frozen not by cold or force, but by the relentless gaze of inquiry. Now, let us take this microscopic curiosity and extrapolate it to a scale that borders on the mystical. Our universe, in its current form, is remarkably stable. The fundamental constants are fixed, the laws of physics are consistent, and the cosmic structures from galaxies to atoms persist. But what if this stability is not a given? What if the universe, at some deep level, is inherently unstable? prone to quantum fluctuations that could, in theory, unravel its very fabric. The wild speculative leap of the quantum Zeno effect asks a staggering question. Could the universe be held in its current, life-permitting state by a form of constant observation? Is there a universal consciousness, a pervasive awareness that by its very act of perceiving reality performs a cosmic version of the Zeno effect, freezing the cosmos into the familiar patterns we know? In this view, our own individual acts of observation would be mere fragments of this grand, sustaining attention. The universe exists in its stable form because it is being watched. The moment that attention were to cease, the underlying quantum probabilities might take over, leading to a rapid decay or transformation into something utterly alien and unrecognizable. This is, of course, a vast and untestable analogy, pushing a laboratory effect far beyond its reasonable limits. The quantum Zeno effect works on specific, isolated quantum systems with a clear initial state. The universe as a whole is neither isolated nor clearly in a single quantum state we can measure. The idea of a universal consciousness is a metaphysical concept, not a scientific one. Yet, as a thought experiment, it forces a fascinating inversion of our relationship with reality. We often think of consciousness as a late-arriving passenger in a pre-existing cosmos. But the Zeno logic suggests a symbiotic, even necessary relationship. Observation is not a passive reception of data, it is an active intervention that maintains order. It paints a picture where the act of seeing and the thing seen are locked in a dance of mutual preservation. The universe gives rise to observers, and those observers, simply by being aware, might be the gentle hand that keeps the universe from falling apart. It is a poetic and humbling idea that our collective attention, our wonder, and our very consciousness might be the quiet, constant force that holds the stars in their courses and the ground firm beneath our feet, simply by bearing witness to the magnificent fact that they are there at all. The universe may not be waiting for anyone to look. There exists a theory that cuts through the paradox of the observer entirely, proposing that reality solidifies on its own through a built-in cosmic ticking clock. This is the theory of objective collapse, most famously articulated by physicists Garodi, Rimini, and Weber, known as the GRW model. It dares to suggest that the wave function, that haze of quantum possibility, does not need a conscious mind or even a measuring device to collapse. It collapses spontaneously, randomly, and inevitably as a fundamental feature of the universe itself. The mechanism is both simple and profound. Imagine every particle in existence, from the electrons in your eyes to the photons from distant stars, is constantly subjected to a tiny, random chance of spontaneously localizing. In the GRW model, this chance is incredibly small for a single particle. A given electron might undergo such a spontaneous collapse only about once every 100 million years. When it happens, the particle's wave function, which might have been spread out over a range of possibilities, suddenly shrinks or localizes to a definite position in space. It is as if the universe, at random intervals, gives a gentle but decisive tap to each particle, asking it to please decide where it is. On its own, this rare event for a single particle would change nothing about our macroscopic world. But consider an object you can see and touch, like a coffee mug on a table. That mug is made of trillions upon trillions of atoms, each with their own cloud of electrons. In the GRW picture, these particles are weakly linked through their interactions. The genius of the theory is in the amplification mechanism. When one particle in a large system undergoes a spontaneous collapse, it can trigger a chain reaction, causing the entire entangled system to collapse almost instantly. The chance for a single electron to collapse spontaneously is minuscule, but the chance for any one of the countless particles in a mug to collapse in a given millisecond becomes overwhelming. Thus, the quantum fuzziness of the mug's constituent particles is constantly being pinned down to definite positions, ensuring the mug itself always has a definite location. It never exists in a superposition of being on the table and on the floor because its parts are being continuously and objectively forced to choose. This theory introduces a new fundamental constant into the laws of physics, a parameter that sets the rate of these spontaneous collapses. It is a number that balances two scales, ensuring single particles behave in the strange, probabilistic way we see in quantum experiments, while large objects behave with the solid definiteness of our everyday world. The boundary between the quantum and the classical is not drawn by consciousness or complexity, but by size and the relentless, random ticking of this universal clock. Objective collapse directly targets the measurement problem, offering a clean, physical solution. In Schrödinger's thought experiment, the radioactive atom, the Geiger counter, the poison vial, and the cat are all part of one large quantum system. According to GRW, within a fraction of a second, some particle in that vast system will undergo a spontaneous collapse, forcing the entire setup to resolve into a single outcome, alive or dead, long before any human opens the box. The cat is never in a true superposition because the universe itself does not permit such large-scale ambiguity to persist. It is always one or the other, decided by an objective, random process woven into the fabric of reality. This paints a cosmos that is neither passively observed nor branching endlessly. It is a universe that is constantly crystallizing, moment by random moment, from the bottom up, its definite reality emerging not from our gaze, but from an intrinsic, granular rhythm written into the heart of matter. The universe crystallizing from random collapse suggests a reality built from tiny, definite events. But what if the events themselves are not the foundation? What if they are merely the output of a deeper, more fundamental process? This leads us to a vision of reality that strips everything down to its most essential ingredient, not matter, not energy, but pure, shimmering information. The idea is captured in a powerful phrase coined by physicist John Archibald Wheeler, "it from bit." In this view, every particle, every force field, every moment of spacetime derives from a bit, a binary answer to a yes or no question posed by the universe. But to grasp the full, breathtaking scope of this, we must upgrade from the classical bits of our everyday computers to the quantum bit, the qubit. A classical bit is a switch, either definitively 0 or 1. A qubit exists in a superposition of both states simultaneously, a blend of possibilities. It only snaps into a definite 0 or 1 when measured. This quantum nature is not a bug, it is the feature that might build our cosmos. Imagine the fundamental layer of reality not as a seething foam of particles, but as a silent, vast ocean of qubits, an unfathomable number of them, each humming in a state of pure potential. The laws of physics, from gravity to electromagnetism, are not written in stone. They are the algorithms, the consistent rules of interaction that govern how these qubits become entangled, interact, and finally, decohere into definite answers. Our universe in this radical picture is not a place. It is a process, a specific, ongoing quantum computation being run on the hardware of existence. What we perceive as the flow of time is simply the sequential processing of this cosmic program. The expansion of space, the formation of galaxies, the dance of particles in a lab, all of it is the real-time output of a calculation of unimaginable complexity. This reframes the very nature of the multiverse. If our universe is one specific program, one particular algorithm running on the quantum computer of reality, then other universes are simply other programs. The cosmic computer has near infinite processing power. It can run countless simulations in parallel, each with its own initial conditions and rule sets. Some programs might instantiate universes with 4 spatial dimensions where gravity operates inversely. Others might generate realities where time flows in loops or where the concept of separate objects never emerges. Our home universe, with its 3 dimensions of space and 1 of time, its specific constants and forces, is just one executable file among a near-infinite library. The fine-tuning problem finds a new context here. We do not live in a special universe. We simply inhabit a program whose algorithmic output happens to generate stable structures like atoms, stars, and conscious observers capable of wondering about the code. Most other programs would output sterile, chaotic, or instantly collapsing realities, cosmic error messages that flash into and out of existence in a Planck time. This quantum computational view elegantly bridges many of the theories we have explored. The holographic principle fits perfectly where the three-dimensional world is a projection from a two-dimensional surface rich with quantum information. The simulation hypothesis gains a more rigorous foundation, not as a game run by aliens, but as the intrinsic nature of a reality built from information processing. Even the strange results of the double-slit experiment make a new kind of sense. The particle's path is not determined until it is measured because the cosmic computer does not need to render a definite outcome until a query, a measurement, is made. It is the ultimate optimization, calculating only what is necessary for the consistency of the program. So what is the nature of this ultimate quantum computer, and who or what wrote the first line of code? Science has no answer, and perhaps the question is meaningless within the program itself. The computer may not be a thing in space, but the very substrate of existence, with the code and the hardware being one and the same. We are not users of this system. We are patterns within its output, transient arrangements of quantum information that have become complex enough to partially decode the very processes that gave rise to us. Every thought you have, every sensation you feel, is not just a product of this computation. It is the computation, a fleeting, beautiful subroutine in the cosmic code, momentarily aware of its own existence. Yet if the universe is a quantum computation, it must have rules to prevent catastrophic errors in its own logic. Stephen Hawking, looking at the equations of general relativity, noticed a terrifying possibility. The math allowed for solutions that described closed time-like curves, paths through warped spacetime that loop back on themselves, effectively creating a tunnel into the past. A wormhole, if stabilized, could become such a time machine. The implications were horrifying. What if someone went back and prevented their own birth? The grandfather paradox would rip causality apart, creating logical inconsistencies that could unravel the very fabric of reality. Hawking found this so unsettling he proposed not just a theory, but a cosmic safeguard. He called it the chronology protection conjecture. It is the idea that the laws of physics, though they may permit time travel in their abstract equations, contain hidden mechanisms that actively prevent it from ever happening in practice. The universe, according to Hawking, seems to have a built-in immune system against paradoxes, a series of physical fail-safes that kick in to protect the orderly flow of cause and effect. One of the most promising candidates for this protection comes from the quantum vacuum. Empty space is not truly empty. It is a seething, bubbling sea of virtual particles, constantly flickering into and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This quantum foam is normally invisible, its effects subtle. But when you try to create a wormhole or warp spacetime into a closed time-like curve, you are stretching the fabric of reality to its breaking point. In that extreme environment, the gentle quantum foam turns into a raging storm. The process is known as vacuum polarization. As spacetime is bent toward allowing a time loop, the virtual particles in the vacuum become highly polarized. They align in such a way that their collective energy density skyrockets, flooding the nascent time tunnel with an incredible surge of negative energy. This isn't just a minor obstacle. The calculations suggest this negative energy feedback would grow without limit, becoming infinite at the precise moment the closed time-like curve is about to form. Imagine trying to blow up a balloon that has a tiny, self-sealing hole. The harder you blow, the more air rushes out of the hole, making it impossible to ever fully inflate the balloon. The quantum vacuum acts like that self-sealing mechanism. The more you try to warp spacetime to create a time loop, the more negative energy the vacuum generates, which further warps spacetime in the opposite way, collapsing the tunnel before it can become stable. It is a perfect automatic feedback loop of destruction. The energy required to overcome this quantum barrier would be infinite, a physical impossibility. So time travel to the past isn't merely difficult or dangerous, it is fundamentally forbidden by the universe's own quantum rulebook. The conjecture paints a picture of a cosmos that is fiercely protective of its own history. It suggests that causality isn't just a convenient pattern we observe, but a deeply embedded principle that reality will defend at all costs, even if it means summoning infinite energies from the void to crush any potential paradox at the moment of its birth. We are left with a universe that allows for breathtaking possibilities in theory, but in practice draws a firm, uncrossable line around the past, ensuring that history remains a singular, inviolable story, forever safe from meddling travelers. The universe's stubborn refusal to allow paradoxes safeguards our history, but it leaves us with a deeper, more persistent riddle. Why does our reality seem so perfectly, improbably crafted for our existence? This is the fine-tuning problem, and the multiverse offers one of its most compelling and controversial answers. The numbers that govern our cosmos are not arbitrary. They are precise dials, and if any were turned even slightly, life as we know it would be impossible. The strength of gravity, the mass of the proton, the energy in empty space, the cosmological constant, each one sits in a breathtakingly narrow window of viability. If the strong nuclear force were just a few % stronger, hydrogen would fuse into helium so violently in the early universe that all stars would burn out in a cosmic flash, leaving no time for planets or life to form. If it were slightly weaker, hydrogen would never fuse at all, and the universe would be a featureless sea of the simplest element, with no heavier atoms for chemistry, no rocks, no water, no us. The cosmological constant, which drives the accelerating expansion of the universe, is tuned to an accuracy of 1 part in 10 to the power of 120. That is a decimal point followed by 119 zeros and then a 1. A number so preposterously precise it screams for an explanation. It is as if a cosmic locksmith crafted a combination lock with 120 dials, and every single one landed on the exact digit needed to open the door to a living universe. Faced with this staggering improbability, we have few options. One is to invoke a cosmic designer, an intelligence that set the dials. Another is to propose that these constants are not free parameters, but the inevitable outcome of a deeper, unified theory we have yet to discover. But the third, and perhaps most scientifically popular option today, is to invoke the multiverse. In a truly vast, perhaps infinite, ensemble of separate universes, each with its own randomly selected set of physical constants, every possible combination will be realized somewhere. Most of those universes will be stillborn, cosmic deserts where forces are too weak to bind atoms or too strong for anything but black holes. They will be silent, dark, and empty. But in a tiny, tiny fraction of the cosmic lottery, the numbers will, purely by chance, fall into the life-permitting range. We, of course, can only find ourselves in one of those rare, hospitable bubbles. Our astonishment at the perfect tuning is therefore an illusion of perspective, a form of cosmic survivorship bias. We are not lucky winners of a 1 in a Googleplex lottery. We are the inevitable inhabitants of the only kind of universe we could possibly observe. This statistical argument is powerful and elegant. It turns a metaphysical puzzle into a simple matter of probability in an infinite sample space. It fits seamlessly with the cosmic inflation multiverse, where each bubble universe nucleates with random constants, and with the string theory landscape, where each valley represents a different vacuum state with its own physics. The multiverse does not explain why the constants are tuned for life. It explains why we perceive them to be tuned. It is a cosmic anthropic principle in action. Yet for all its explanatory power, this solution leaves many scientists deeply uneasy. The core of the scientific method is testability, the ability to make predictions that can be confirmed or refuted by observation. The multiverse, in its most general form, risks being a theory of everything and therefore nothing. If every possible universe exists, then it predicts that we should observe a universe compatible with our existence, which we do. But this is a tautology, not a falsifiable prediction. How could we ever prove the existence of those other sterile universes? They are, by definition, beyond our cosmological horizon, forever disconnected from our spacetime. Any evidence we might claim, like strange patterns in the cosmic microwave background from collisions with other bubbles, would be indirect and hotly debated. To its critics, invoking an infinite unseen reality to explain the peculiarities of our own can feel like a sophisticated cop-out, a retreat from the traditional goal of physics to find a single, elegant, and necessary set of laws for our one and only universe. It replaces the mystery of fine-tuning with the perhaps greater mystery of an infinite, unobservable meta-reality. Are we embracing a profound new paradigm of existence, or are we simply giving up on finding a deeper reason for our own? The multiverse answer to fine-tuning stands at a razor's edge, a brilliant statistical insight that simultaneously solves a profound puzzle and questions the very nature of what a scientific explanation can be. The fine-tuning of our cosmos points toward a hidden unity, a single set of rules from which all of reality's strangeness flows. For over a century, physics has been split by a civil war. On one side, quantum mechanics governs the realm of the impossibly small with breathtaking precision, a world of probability and paradox. On the other, Einstein's general relativity masterfully describes the cosmos at its grandest scales, where gravity is the curvature of spacetime itself. Both theories are magnificently successful in their own domains, but they are written in mutually incomprehensible languages. Where they meet at the center of a black hole or the first instant of the Big Bang, their equations explode into nonsense. This divide is the greatest unsolved problem in fundamental physics. The dream is a theory of quantum gravity, a single framework that seamlessly weaves these two visions into one, revealing the true, unified fabric of existence. And when we finally glimpse it, the reality it describes may be so alien that all our current models, from many worlds to holograms, will seem like crude sketches of a masterpiece. Imagine trying to understand a forest by studying individual leaves with one microscope and the entire canopy with a completely different telescope. You would have two brilliant but disconnected descriptions. Quantum gravity seeks to be the theory of the tree itself, explaining how the leaves and the canopy are born from the same trunk and roots. The challenge is profound because the core principles of the two theories seem to contradict each other. Quantum mechanics is built on uncertainty, randomness, and discrete packets of energy. It thrives in the flat, static stage of space and time. General relativity, in contrast, is deterministic and smooth, describing a dynamic, flexible stage that is itself the actor, warping and curving in response to mass and energy. To unite them, we must ask, what is spacetime made of at the scale of a billionth of a billionth of a billionth of a centimeter? Is it a smooth fabric, or is it granular, built from tiny, indivisible quanta? The leading candidates, like string theory and loop quantum gravity, offer wildly different answers, but they hint at a shared, startling possibility. The unified reality may have no fundamental space or time as we experience them. Space and time could be emergent phenomena, collective illusions that arise from something more basic. Think of the smooth, continuous surface of a lake. From a distance, it seems like a perfect sheet, but up close, you see it is made of countless discrete molecules of water, constantly moving and interacting. The lake's surface is not a fundamental entity. It is a useful description of the collective behavior of its parts. In the same way, our flowing experience of time and our three-dimensional arena of space might not be the foundation. They could be the calm surface that emerges from a frenetic, hidden quantum substrate. What could that substrate be? One possibility is a timeless, spaceless network of pure relations. In this vision, the universe is not a container where things happen. It is a vast web of events like knots in an infinite net connected by relationships. An electron here and a star there have no independent meaning. Only the connections between them define their existence. Properties like position and momentum are not inherent. They are derived from the pattern of links in the web. Causality itself, the unbreakable chain of cause and effect, might not be a fundamental law, but a habit that emerges in this network as it grows in complexity. Much like the rules of traffic emerge from the collective movement of individual cars, not from any single vehicle. This would mean that at the most fundamental level, the universe is not located anywhere, and it is not evolving through time. It simply is a static, breathtakingly complex structure of correlated information. Our journey from past to present to future would be a kind of cognitive illusion, a path our consciousness traces through this eternal structure. The Big Bang would not be a moment in time, but a particular region in the web, a dense knot of relations from which our perceived timeline unfolds. This is a universe where becoming is an illusion and being is the only truth. It is a vision that echoes the implicate order, but grounded in the hard mathematics of quantum geometry. Other paths suggest a reality built from quantum events where spacetime itself is pixelated. In loop quantum gravity, for instance, space is woven from tiny, vibrating loops. There is a smallest possible volume, a quantum of space, and a smallest possible tick of time. In this granular landscape, the smooth continuum of general relativity is an approximation, valid only when you zoom out. At the Planck scale, the universe might resemble a dynamic, constantly updating neural network, with each quantum of space acting like a neuron, firing and influencing its neighbors. Gravity would then be the curvature that emerges from the collective excitement of this cosmic network, much like the idea of a wave emerges from the collective motion of water molecules. Reaching this theory is the final frontier of fundamental physics. It is not merely an academic exercise to tidy up our equations. It is a quest to answer the most basic questions we can ask. What is reality at its absolute core? What happened at the very beginning when all the energy of the cosmos was compressed into a volume 1 trillion times smaller than a single atom? What is the ultimate fate of a black hole's interior? The theory of quantum gravity holds the keys to these mysteries. It promises to show us the universe without the comforting illusions of space and time, revealing a foundation so strange that our language, built from the experience of a middle-sized world, may fail to describe it. We are like flatlanders, beings who live in a two-dimensional plane, trying to comprehend a three-dimensional sphere passing through their world. They would see only mysterious circles appearing, growing, and shrinking. Our current theories are brilliant descriptions of those circles. The unified theory will be the shocking, beautiful revelation of the sphere. This final vision asks us to consider the most intimate mystery of all, the nature of our own awareness. What if consciousness is not a rare accident of biology, but a fundamental feature of reality itself? This is the theory of panpsychism, the idea that mind is as basic to the cosmos as mass or electrical charge. It proposes that some form of experience, however simple, exists all the way down. An electron may not think or feel joy, but it might possess a faint, intrinsic spark of inner life, a raw, elemental awareness. In this view, the universe is not a dead machine that somehow generated a ghost. It is, from its very inception, alive and awake. The complex consciousness of a human or an animal is not created from inert matter, but arises when these fundamental mind-like properties are organized into sufficiently complex systems, like a symphony emerging from the combination of countless individual notes. This perspective reframes the entire quantum narrative. We have explored how observation seems to play a role in shaping reality, from the Copenhagen interpretation to the participatory anthropic principle. Panpsychism offers a substrate for that participation. The famous quantum indeterminacy, the inherent randomness at the heart of every particle, might not be mere chance. It could be the elemental freedom of a universe with proto-conscious properties, a tiny wiggle room for spontaneous action. If the basic constituents of reality have a hint of interiority, then the universe's evolution is not a blind, deterministic grinding of gears. It is a process with an inner dimension, a form of learning or exploration through trial and error. Each quantum event is not just a random tick, but a micro-choice made by the fabric of existence itself. Over cosmic scales, these countless micro-choices could guide the evolution of structure, favoring pathways that lead to greater complexity and richer forms of experience. The universe evolves not just physically, but in its capacity for feeling and knowing. This leads to the most profound extrapolation of the idea. If consciousness is woven into the fabric of everything, then the cosmos as a whole, the vast network of galaxies, stars, and dark energy, might itself be a conscious, self-perceiving entity. We are not separate observers looking at the universe from the outside. We are localized expressions of the universe's own growing self-awareness. Your thoughts, your wonder as you gaze at the night sky, are not happening inside a brain that is inside a universe. They are the universe in one particular region organized as a human brain, thinking about itself. It is a cosmic mirror loop where the universe creates pockets of complex order that can reflect back on their own origins, closing the circle of perception. In this living universe, the fine-tuning for life is not a statistical fluke or a programmer's choice. It is the natural inclination of a cosmos that is inherently oriented toward the blossoming of experience. The laws of physics are not arbitrary rules, but the stable habits of a vast mind, the consistent patterns that allow for a coherent story to unfold. The search for a unified theory of quantum gravity, then, is not just a search for equations. It is an attempt to read the thoughts of the cosmos, to understand the deep grammar of a universal consciousness expressing itself through spacetime and matter. This is where our journey through 30 quantum realities ends, not with a definitive answer, but with the most humbling and majestic question of all. We have moved from countless branching worlds to a single, self-aware whole. Perhaps every theory we have explored, from the many worlds to the hologram, from the simulation to the implicate order, is a different facet of this one unimaginably profound truth, that the universe is not just stranger than we suppose, but more alive, more connected, and more intimately aware than we have ever dared to dream. We have traveled from the fragile probabilities of a single particle to the infinite echoes of an eternal multiverse. These 30 visions of existence, from the many worlds to the conscious cosmos, are not proven truths, but the breathtaking frontiers of human thought. They are our species' boldest, most imaginative responses to the profound and unsettling weirdness revealed by a century of quantum discovery. Each theory is a different lens, trying to bring into focus a reality that fundamentally resists our everyday intuition. Whether you find the holographic universe elegant, the simulation hypothesis unsettling, or the participatory principle empowering, they all share a common purpose: to stretch our minds beyond the comfortable solidity of the world we perceive. So, which of these quantum realities resonates with you? Does the idea of endless branching selves feel liberating or lonely? Does a universe built from information seem more or less real? Share your thoughts in the comments below. This conversation is only as rich as the perspectives we bring to it. If you crave more journeys to the edge of understanding, be sure to subscribe. The cosmos is full of mysteries waiting to be unraveled, And the greatest adventure lies in never ceasing to ask what is truly real.